Alright, I'm going to try to do something different today. I am going to do a Leetcode problem. Maybe more than one. Yeah, right, let's see. So, a little bit of background. I do Leetcode problems from time to time because I enjoy them. I do work in software and they kind of keep me on my toes and they kind of keep me sharp for in case that I ever have to jump ship and do an interview somewhere. Maybe like a Fang one day. I don't know. But anyway, yeah, I've done quite a few of them. Not as many as I'd like, but I try to make some time every day to do them. So I decided to try to make some videos of me actually going through them and maybe talking through my process of doing them. I'm not a competitive coder. I would like to be, maybe, because it's actually fun. It can be fun, but I need a lot more practice personally. So um, I just felt like, since I'm doing these, and it's my time, I should maybe make videos of me doing them. I know there's people who do these problems online, and they're like a lot sharper in that area, but you know what? Practice makes perfect, right? And why not make a video about it? Okay, so um, let's see, what would be a good problem to start off with? Okay, I'm going to start off with a tree problem. You can't go wrong there. Well, you probably could. I mean. So let's just start with an easy one. See, I've done a bunch of these already. Design, and this check means that you've passed them. So, but you know what? I'm gonna go through one that I probably did already. And by the end of this video, I'm gonna tag this as the definitive problem that I choose. So, count good nodes in a binary tree. Let's see what this is about. All right, I'm gonna do these in Python because why not? Python 3 because I get my little f strings. Okay, given a binary tree root, choose a node x in the tree is named good if in the path from root to x there are no nodes with a value greater than x. Return the number of good nodes in the binary tree. Okay, so a node x in the tree is named good if in the path from root to x there are no nodes with a greater value. So this is a binary tree, a regular binary tree. It's not a search tree. Something to note. Okay, so the traversal is going to be standard kind of DFS without comparing keys. Well, maybe some other type of traversal, but okay. So there are no nodes that are good. Okay, so basically, the nodes that are good are the reason why 3, 4, and 5 and 3 here are good is because none of these nodes are greater than in these paths are greater than their parent. A node X in the chain is named good. So what are you? Let's see what the inputs are. Okay, the input is the tree, and the output is 4. Okay. So basically, what I think I can do is, Oh, I'm not also another note here. I may not be putting the most efficient solution here, so I'm getting better with these over time. So let's see how this works out. So I imagine a DFS is something I would start off with, and so like in this case, 2 is not good because 2 is smaller than 3 and it's lower on the hierarchy, right, than 3 is. So. I mean, I guess the standard way of might be doing this is that, okay, so I pass in root. So I'd want to try to keep all of my paths, sort of, right? I want to keep my pathing going on. So the first thing I would think, the simplest, most brute force-ish kind of solution would be to traverse these nodes here, traverse these trees, and just keep checking recursively if I have nodes that are greater than if I have nodes that are greater than the root subsequently going down. So essentially I did 2 DFSs, right? Like a nested DFS. That would be, I know that we could probably, I'm thinking we can probably do some sort of hash solution here, but let's just check it out. Okay. So I'm going to call this, I might get rid of this here, call it DFS2. self root. Okay, so basically, if I have my root value, and actually maybe, so let's try to think about this. What might be a good way to do this? Should I go bottom up, meaning I do a pre-order traversal, or rather post-order traversal, and then check this node against the parent node? I guess maybe. Could be. I don't know. Let's just try something. Okay, so if root equals none. By the way, I haven't done a video like this where I'm doing the live algorithm coding, so these will get better. If root equals none, then we want to return. Okay, 0, because there's no good nodes. If root, so remember, how do you tell if a node is good? If it's less than its parent, right? And it's less than every ancestor of its. So, I said one way we could do this is we can maintain every ancestor, right? All right, let's try to let's see. There are no nodes in the path from root to x. Okay, so remember, this is the path from root to x. So, this path can be windy, so we're just looking at all the ancestors. So, basically, what we want to do, parent, or ancestor, let's call it path, right? How do we maintain the path? Okay, we can keep appending to the path, I think. Let's have a set, maybe, right? So we can check the path. Path, okay. Okay, let's try to say for node in path if root dot val is less than path is less than node dot val greater than node dot val. What do we do? If root dot path greater than node dot val, or less than node dot val, we want to break. Okay. Let's see. Because this is roughly how we do it. You just have to figure out how to record the path properly, right? So, I mean, we could also get all the paths, right? Like, that's not a big deal. But anyway, if root.val is less than node.val, all right, let's try greater. So path. Well, first let's figure out how to get to path. Path. Okay. Path equals path dot root. Okay. Path equals root. Let's just try to. Okay. Root.val. What we're gonna do is we're gonna append. We're gonna increase the path. Okay. Let's call. path equals new path equals I in path. Let's call it yeah, this looks right, so I'm gonna do this. New path append root.val. Okay, so at this point what we're gonna do is we do dfs root.right new path self.dfs new path. Okay, so what we're doing is we're just copying a path, right? Because these path variables can, these are paths can change, right, from place to place. Well, let's first, you know what? Before I go down into it, what I want to do is I want to check if our pathing strategy looks right. Okay. So first we do self.dfs. Let's do that. And I want to get all my paths. All right. Paths. Okay, and I'm going to paths.append new path. So I want to append all the paths that went to the leaf. Let's just try that, see what happens. Print paths. Paths. That was new path references for us. Oh, okay. Okay, you want to append path. Okay. Okay, so 3, 4, 5, 3, 4, 5, 3, 4, 1, 3, 4, 1, 3, 1 has 3, 1 a path. 3, 1, 3, 3, 1, 3. I don't know how 3, 1 is a path. I mean, 3, 4, 1, 3, 3, 1, 3, 3, 1, 3, 3, 4, 5, 3, 4, 5 is a path. Oh, okay, 3, 1's a path because yeah, I see why. Okay, so let's just say that we want to get all the paths, okay? New paths, let's try paths.append path. Okay, let's try this. Now this should have a lot more. Oh boy, not really. All right, let's try this. I'm just gonna append paths the whole 9. Okay, so this is like every path there. You get 3, you get 3, 1, 3, 1, 3, 1, 3. Okay, so remember, this has to be in order, right? So how do we assure order here? 3, 4, 1, 3, 4, 5. Okay, so okay, so so what we could do, let's have paths as okay. For I in path, okay, for node in path, node for node in path, append root.val. Okay. What if I just what if we just create a new path every time? It's not gonna work. All right, so we want to make sure we get all the nodes from all the other paths, and we want to append root.val. Okay, so I in new path for node in new path. So this is where we want to do the check. Node equals 0. What's the best way to write this? For node in new path, let's try 1. If node.val is greater than equal to root.val, basically everything that's before it, then good node equals 0, break. Right, so we start with a 1, right? Return good node plus. Okay. Node.val. What? Okay, so print good nodes. Let's try print good nodes. Good nodes. Let's just assume that this is working. Okay. So output. So return good nodes. Return good nodes. Okay. Wow, 32 milliseconds. I'm pretty sure that's not going to pass. But you know what? Whatever. Let's try it again. All right, accepted. And let's just try 1. Ideally, I would like several test cases to work. You know, I mean, we try to. Okay, let's see what happens. We're gonna try running this sucker here. Okay, see, it worked. It solved the problem. So basically, what it is, all I did was check the paths. Now let's check how we can optimize this, right? Because while this solution, passed, it's definitely not going to pass an interview. Okay, let's check what's wrong with this first of all. Okay, here for node and path, right? We can cut this off early, right? I think we can. If we search through this node here, right? Like we're doing this 2 for loops here, okay? So instead of doing that, let's check for node in path. good node. Now here's the thing. Let's check. Let's understand what the deal with these good nodes are. Okay, good nodes can be deeper than bad nodes. All right, so we can't just quit traversing easy early. So we have to keep traversing. So for node and path, if okay. Node, new path. Okay, we'll start there. Node, new path, append node. If root better than okay, and then we want to at the end new path dot append root. Okay, so it's this improvement, right? So we don't want to break either here, right? Because we need to construct the whole path. So let's see how much better this does. First of all, let's check if this even works. All right. Okay, let's go back to our first example. So what you saw that I did was new path that append. So I passed the trivial case because I was using the wrong brackets. It's not supported. Okay, node.val. Let's just put integers so we don't store a bunch of extra crap in there. Okay, cool. And that took 36 milliseconds. It's slower than I expected. And then 32. Let's try running and see what happens. Oh, we're still pretty crappy. Okay, so here's the deal. Do we even need these paths? Let's check if we need these paths. I don't think we need these paths, so let's get rid of these paths here. We just printed the paths so we can kind of print them out, but we don't need to append a path to the path. Okay? So we know that our paths are working, so let's do this. Whoa. Why? Oh, okay. Where is paths not defined? We don't need you anymore, paths. Okay, the space constraints went down. Okay, great. So, need this path. Get rid of this extra list. Whoa, what happened there? That's kind of odd behavior. Let's try running again. What happened? When I had that... All right, well, okay, so let's check what's going on here. So, new path append root.val. Okay, so something tells me this checking of the paths is what's causing the time delay and the extra space. So let's just assume that we don't have to check the paths, okay? How can we avoid doing that? How can we avoid checking each new path as we traverse through it? Well, what if we, I mean, what we could do, we know that every node that goes down the tree has to be larger than all the previous nodes, right? In order, so if that's the case, we could probably, instead of a list for the path, let's try to do a priority queue. Import heap queue. Heap queue. So here's the deal with this one. Here, the priority queue. Okay, no, we don't need a priority queue. Screw that. Let us try to maintain our maximums, okay, instead of the path. Okay, so let's say max. Let's say if this does it. Max equals 0. In path. Okay. So what we want to do max in path. Okay. If root dot val greater than max in path, right? Good node equals 1. Else good node equals 0. Something tells me right off the bat this is not going to work, but let's give it a shot. Okay. Remember, root.val greater than equal to. All right. Okay. So what we're trying to do here, if the current root is greater than max in path, so remember what we have to do is max in path. You have to reassign max in path equals max root.val max in path. All right, there we go. Submit. Oops, wrong number. Why? Let's see if we can get the wrong answer with another one. Yeah. Okay, wrong code. Accepted. See, that first one was accepted. I bet this one's going to be accepted. Yep, that's accepted, and that's accepted. So what does it not like about this one case that we tried? Let's get back to that case that it failed at. Okay. Let's throw this case in here. So what could be the problem? Let's try that with this tree visualizer. -1. Oh, yeah, duh. Let's see. Python min value. Here's the problem. Min infinity. Let's see how to get it min infinity. All right, because the thing is we're starting at 0. That's probably the problem. So we want to set the first value not to 0, but to min infinity. What is this? Okay, there you go. And there you go, slightly faster. Okay, slightly faster than 10%. But see, here's the crazy thing. I bet the thing is we can do this iteratively, and that's where we'd save all the space. Okay, better than going through each path. All right, it double the speed actually, or half the speed. Well, double the speed, half the runtime. But we are still recursively iterating. So why don't we try? How can we speed this up so we don't have to look through all these? I bet. Well, you know what? I'm happy with this solution for now because this is a working solution with O of n performance, right? That's something that we can. It's O of n, right? I assume that there might be some log n solution here, but let's try keeping this for now. So I like to annotate the things that I work on. How am I going to say? Okay. The max value, so we iterate through the tree. We maintain the max value as we iterate through the tree in a DFS manner, we keep checking if the root is greater than the max value seen so far, and that informs us that it was a good node. Let's see, accepted Python solution, count good nodes in binary tree. We reassign max value upon each iteration. So one important thing to note, let's call it DFS. DFS, simple solution, I like that. And sure. Okay, so one thing to note here with this solution. One thing to note with the solution, all right, is that max and path changes, right? Because the thing is, there's a trick in Java where you can maintain the max overall through the entire iteration by having an object. Python, because you know, and in Java this would work too, but in this case we're passing an integer, so basically this integer is going to pass through the particular path that you traverse, but it's not going to be aware of the entire tree. So that's why this path value integer here was good for looking through the specific, for our algorithm, looking through the specific traversal path for each instance of a node, right? And it would change as the path continues along each of its directions, right? Okay, but it wouldn't be aware of all the other values as we traverse through the tree. But that's another nice trick if we needed to do that. Okay, so let's see what is some of the solutions that people have. That's what I just put there. Okay. Java. Let's see what's up with Java. Good nodes until count. Huh. Okay. This is pretty much doing exactly what I did, so I don't know why. Let's see Python one-line recursive. Good nodes 1. Oh, I don't like this inner nested function. Typically not easy to test an inner nested function, so I don't know, but there may be use cases you wanted, but in unit test, I mean. Okay, let's see where this solves some, where this saves some time, essentially, because I don't see it really saving some time. I mean, I guess it's saving because it's not doing one of the DFSs, because there's recursive solve function, you know, but I don't know. Anyway, we can look into this later. Let's move on to another problem. Okay. So, what's the next? Okay. Problems. I did a tree problem. I'm not going to do a dynamic programming problem right now because I wanted to. Oh, by the way, this video is probably long as heck already. So I wonder how much. Whoa, 2.8 gigs. It's going to be a huge video. What else? Okay, so let's try something not too taxing for tonight. I'll call it. Oh, the topo sorts. Those are always fun. Rolling hash. What is this? This is a whole new category of problems, huh? The string, and they start off by Oh, this is like windowing problems. Okay, no, not tonight. Um, Ordered map geometry. Wow. Okay. When I used to come on this site, I didn't see so many dissections here or sections. Let's do a hash map problem, a hash table. These are fun. I mean, they all, like you can even do some of the hard problems and they're like reasonable, right? But obviously, like I'm in the middle usually with these. So let's see, rabbits in forest. And we'll try a 55%. I like these problems because I can usually wrap my head around how to do these. Okay, in a forest, each rabbit has some color, some subsets of rabbits, possibly all of them, tell you how many other rabbits have the same color as them. Those answers are placed in an array. 2 rabbits answered 1 could be both the same color, say red. The rabbit that answered 2 can't be red, or the answers would be inconsistent. Say the rabbit that answered 2 was blue, then there should be 2 other blue rabbits in the forest that didn't answer into the array. The smallest number of rabbits in the forest is therefore 5 to 3 that answered plus 2 that didn't. Okay. Let's see if we understand this. 1, 1, 2. The minimum number of rabbits. Why could there be 5 rabbits? Is the minimum in this forest. Okay. Each rabbit has some color. Some sets of rabbits, possibly all of them, tell you how many other rabbits have the same color as them. So basically, the first rabbit's saying 1 rabbit has the same color. The second rabbit is saying 1 rabbit has the same color. So that means that these have to be 4 rabbits. These have to be 4 rabbits, right? Because they're saying 1 other rabbit has the same color. Well, these could be 2 rabbits, right? But now, if this third rabbit says 2 rabbits have the same color, then the rabbit answer 2 can't be red, or that answers would be inconsistent. So these could be 2, but then this one can't be the same color, right? Why? Because these rabbits are both saying 1, right? Are we saying that the rabbits answer truthfully? Let's assume that the rabbits answer truthfully. So then this rabbit must be speaking of 2 other rabbits, right? How many other rabbits? That's the key word. This could be this one, this could be this one, so these could be talking about the same thing as a minimum. This obviously, though, cannot be talking about the same thing. Then this has to be talking about at least 2 other rabbits that weren't mentioned, right? And this is a subset of rabbits, but possibly all the rabbits, but it, essentially a subset of rabbits, right? Let's just treat it as a subset. So 10 rabbits have the same color. You ask another rabbit, 10 rabbits have the same color. Okay, these could be the same rabbit. This one says 10 rabbits have the same color. Okay, why is the minimum 11? Well, if 10 rabbits have the same color, 1, 2, these could be included, then this says 10 rabbits have the same color. This could be 1 or 2 here in this third one. And this says 10 rabbits have the same color. This could be 1, 2, this could be 1 or 2. Then shouldn't 10 be the answer? A little confused there. Let's see who's looked at this. Hash table math, companies, wish. I don't know what wish is. Alright, you know what? Let's not do a wish problem. I know I'm copying out, but let's try something else. Okay, I am going to do another hash table problem. We are going to not do that one, not do that one, not do that one. Longest harmonious subsequence, set mismatch. This is an easy one. It says 42% acceptance. Powerful integers, word pattern. Count primes, oh boy. Clone an array tree. I already did a tree problem. Clone binary tree, random, find the smallest common element in all rows. This is a medium. It says 75% people get it though, so maybe this will not be too bad. Given a matrix mat where every row is sorted in strictly increasing order, return the smallest common element in all rows. Okay, these are all strictly increasing. Find the smallest element in all rows. So 2, 2, 2 5, 5, 5, yes. Okay. All right. I like problems like this. So let's try. First, what we want to do, we need to do a quick lookup, right? That is evident, okay? So the first thing I think we could do, like let's say this may be a brute force solution, but we can, you know, hashify each of these rows, and then we could literally do a lookup, right? But if we did that, then that would kind of defeat the purpose because we're trying to get away from having to constantly. Okay, I got it. I think. Okay, we have one. We're going to have one map here, right? Okay. We're gonna have a map. All right. Or a set. Let's say a set. Okay. I mean, we could also do priority queues, right? And just pop off the smallest element in each. That, nah, I don't know if I like that. Okay, let's call it a set, right? So, for I in mat, for j in mat I. Okay, so let's just see if this print mat I mat j. J. All right, let's try running this. Row, call, right? Let's do it that way. Row in that. Okay. This is the value of the column. Let's all right, let's try to figure this out. Range I in row. Let's loop by index. Range 0 to length mat. Okay, so first, row call row. All right. Okay, so this should be right. Now what we want to do, okay, so we want to, I'm going to check the 1, 2, 3, 4. Hmm. So I believe we can do this. Okay, so what we want to do is we want to, let's see, print row, row, row. Okay, row 0. Okay, so now we want to add this set mat row call. Set that add. So will that help us? We want to find the common elements in each, right? How do we find the common elements in each? Okay. I think we have to just, okay. Okay. If row, now this is what we do. If row greater than 0, all right. We just simply add. Now, else, now if row is greater than 0, if mat row call in set not in set, continue. Okay. So let's see what the end version of set looks like. Print set. Whoops. Set has no object. Add. Oh, shit. Okay. Now here, now we want to sort this set, right? Else, now we have min. Min equals inf and we have m equals min equal f equals float inf. Okay. Else if s less than, okay, s equals min as m. Okay, so m equals min, print let's see. No, 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 no. No, 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 no. No, we don't want to do that. If mat row call not in S, right? So basically, if the matrix element is not in S, there's no reason to add it. Else, the minimum matrix element we want to add, so we know that matrix row and column is in S, right? Let's try print m. Found. Doesn't sound right. Um, does not seem right. Huh. Let's try. Ah. So essentially, we gotta keep track of the min and get rid of everything. Okay. We need other things. All right, we need to get rid of, essentially, everything in the first row is a candidate for something that's in the second row, right? So when we populate the first row with all the possible candidates, we got to check. We also got to check which of these candidates was not in both sets, right? So we might have to get back to this, but I think we're close here, right? We can, I mean, we know that 5 is pretty much in every set, right? Okay. Let's try this. Whoa. Okay. All right, so what? How much time? Well, we're at 4.6 gigs. A 5 gig video. All right. Okay. I think we're gonna have to cut this short because I am running out of time here. No, it's been almost an hour. Okay, so let's try to add let's say call it set exclusion. E equals set. This is my exclusion set, right? Add E. Okay. Now add mat row call. Okay. So basically I'm creating a new exclusion set here. And then what I want to do for I in S if I not in let's call S is equal to E. All right, let's just do that. E add row column. Let's try print E. Print E. We want At the end of the iteration, we want S to equal the exclusion set, right? Not at the end of each run. Um, so let's start by doing this here. Hmm. Oh, no. We want to, for each row, we want to do this. Dang, this is taking a while. Or it was just some server problems. Let's try printing the exclusion set on each iteration and see what we get from there. I don't want to print down right now. E. Let's try printing E. Let's see. No, do we just need only one? And do we need to... We need to reassign E at the end of this. Okay, I think this is what we have to do. We have to take the exclusion set E equals new set. We have to redefine the exclusion set on each iteration. Let's see what that does. Well, that didn't do what I wanted to do. Let's try. I just want to add the numbers that happen to be common to all these guys. So basically, what we do is we start with s is equal to an empty set, and then on each row. And if the row is equal to 0, oh, 5.3 gigs. We got to finish this soon. If the row is equal to 0, then we just add elements to the set. Then, in the next iteration, if len e greater than 0, s equals e. All right. There we go. That looks about right. And then we get min, m equals min mat row call m. Okay. So basically, this will winnow down the set, I believe, to the minimum element. And let's return min. Whoa, it's not what I wanted to do. I mean, I guess we could. Let's try this. Print E. Let's try printing E. And then we do list E. Result. Sort. And result. So we could say if that'll do it. Mm, mm-mm. Huh. Why would it be? Hmm. Let's try print E. Yes. Okay. All right. So this is it. This is my solution, and I have to say that we got it. However, it probably wasn't the fastest way to do it. Okay. Really, I just have to figure out my logic for not having to worry about this extra list at the end and doing the sort. We can literally keep the minimum element um, all the time of any value that was added to E. Okay. Um, of all the elements that are added to E, you have to always keep pretty much the minimum value that's always going to be as part of E. And I mean, yeah. Okay, anyway, I'm just going to save this for now. And this is basically the solution. No. There's definitely a faster solution, but I'll get better at these over time. So, AC Python solution. Oh, binary search. Could have done that. When I'm searching for an element, that's probably the right answer. Find smallest common element in all rows. Small method. Revisit. Note to self. Revisit. Okay. All right. Okay. So that's it for today. We did 2 problems. It took an hour and 13 minutes, and I'm gonna stop here because damn, that's a lot of stuff. So thanks for watching, and yeah, we'll try some more next time. See ya.